objective of this program on gas well testing is to teach the engineer the proper methods to follow in field testing and interpreting well deliverability tests. In Unit 1, we'll look at conventional and isochronal theories. Unit 2 will cover additional testing options. Unit 3, test design considerations. Unit 4, procedures and regulations. And in Unit 5, we'll look at field test interpretation.
The program you're about to see is hard work. It's going to require your undivided attention. You don't have to take notes. You don't have to refer to the manual now. Just look, listen, and learn. The fellows we see here are about to test a gas well in southern Louisiana. So let's listen in and see what they're planning.
Hey, Alvin, you feel like you've got everything ready to go there?
Yeah, the boys just finished anchoring down the last pit line, so I believe we got it ready.
Okay, good. The casing checked out all right on the backer side there?
We've got a gauge watching it. So far, the pressure's holding stable.
Okay, good deal there. We're going to go ahead and start flowing it on 8 there, and go ahead and let it clean up on it there and see what we've got there.
Okay, about what you figure your final pressure will be on this thing?
We should have around 9,000 there when it cleans up there.
What these fellows are about to do may not be comprehensible to you now, but it should be by the time we finish this program. The testing procedures they are following are based on a solid understanding of gas well flow behavior and good well testing practices. The data they collect will be taken to the engineer's office for interpretations. The interpreted results obtained there may then be used to determine the initial and future deliverability of these gas wells, and in some cases to plan remedial well treatment. Often the test data are submitted to regulatory agencies for its resources assessment studies. Accordingly, our discussion must cover 4 sequential areas. 1. Basic equations of flow. 2. Field testing procedures. 3. Interpretation of field data. And 4. The application of test results. Let's now turn to the first major area of discussion, the basic equations of flow. In our effort to state the equations of flow that apply to the testing of gas wells today, it is incumbent upon us to give credit to those upon whose shoulders we stand. A little history is in order. In the early days, a gas well was tested by opening it fully to atmosphere and measuring its flow rate. These tests were inaccurate because they depended on the size of the wellbore equipment, and they often caused damage because of coning or sand production. In 1936, Rawling and Shellhart of the U.S. Bureau of Mines recommended in the well-known Monograph 7 what has become known as the conventional back pressure test. The foundation of this test is the application of a modified form of Darcy's law to the flow of gas into the wellbore. In this equation, Q sub SC is the flow rate at standard conditions in 1,000 cubic feet per day. P sub R is the average reservoir pressure in PSIA. P sub WF is the flowing sand face pressure in PSIA. And C is a constant for the well. Rawling and Shellhart, drawing upon empirical observations, added the exponent N to Darcy's equation to account for the observed deviation in flow behavior. The deviation is due to several factors, the most important being the effect of turbulence. The range of N is from 0.5 to 1. If we take the logarithm of both sides, we obtain an equation which is a straight line on log-log paper with a slope of n. It has become conventional to plot P sub R squared minus P sub WF squared versus Q sub SC on the log scale, and therefore the straight line will have a slope of 1 over n. In order to obtain a straight line, we need at least 2 points, through which the line may be drawn. Monograph 7 suggests 4 points be obtained to avoid error. The recommended test procedure, then, is to flow the well sequentially, increasing or decreasing at 4 different rates, and measure the flowing sand face pressure, or back pressure for each. Knowing the static reservoir pressure, we can plot the point P sub R squared minus P sub WF squared versus Q sub SC for each measured rate. Draw a best fit line through the points, and obtain the necessary value for 1 over N, then N, and then C. The calculation of N and C is rather direct. The actual test proceeds as follows. After shutting in the well initially in order to reach static pressure conditions, and thereby obtain a value for the reservoir pressure, the flow tests are begun. In order to achieve a given constant rate, the well is flowed through an orifice or critical flow prover at the surface until the pressure stabilizes. It takes some time for stabilization to occur, especially for tight sands. Once a stabilized pressure has been reached, the flowing pressure, usually at the surface, is measured. The well is then flowed at the next higher rate, and the flowing pressure at stabilization for that rate measured. The test is continued until the 4 rates have been measured and the appropriate log-log plot made. Generally, the flowing pressures are measured at the surface. This requires that the measured values of the stabilized pressure at the surface be converted to sand face pressure using appropriate correlations. More about those correlations later. Once we know the values for N and C, or have the straight line plotted on log-log paper, it is a simple matter to determine the absolute open flow potential, or AOF, the flow rate that would occur if the sand face pressure were reduced to 0. Extrapolation of the straight line to the point where P sub R squared minus P sub WF squared equals P sub R squared gives the AOF. Having obtained values of N and C, the basic equation may then be used to calculate the deliverability of a well for any given set of sand face and reservoir pressures. The following example illustrates the procedure. If we know that C equals 0.0037 and N equals 0.93, what is the flow rate when P sub R equals 3000 psia and P sub WF equals 1850 psia? The answer is 6.96 million standard cubic feet per day. What is the AOF? We see the answer is 10.86 million cubic feet per day. Of course, the same results could have been obtained graphically. It should be recognized that only a single rate flow test is needed in order to obtain the back pressure flow equation if the value for N is assumed as known. This is the case, for example, for the single point test allowed by the Oklahoma Corporation Commission. In that particular situation, the Commission allows the operator to assume a value for N of 0.85. Stop the video player now and work Exercise 1 in your manual.
From the exercises you've just worked, you should have learned the foundations and basic assumptions of the conventional gas well testing equation, how a test is conducted, the manner in which rates are measured using orifice meters and critical flow provers, and how to interpret and use the test results. If you have the equations, you have the results, you know the answers. Some of the answers will be coming to you shortly as we proceed along in the tape. For the moment, though, If you understand the material and are confident in your knowledge, then proceed with the tape. If you're not confident, replay the tape to the beginning and start again.
Because the time to reach stabilization in the conventional back pressure test may be long and the flaring of gas excessive, alternative testing procedures were soon recommended. In 1955, Cullender proposed the isochronal gas well flow test. The procedure followed in this test requires a series of flow shut-in periods without the requirement that stabilization of pressure during each flow period take place. The pressure, however, must build up to its static value after each flow period. Details of the isochronal test are given in the course manual. In practice, the well is flowed at 4 different rates, with the duration of each flow period being equal and usually relatively short. Thus, for example, an operator may allow each of the 4 flow rates to last for a period of 1 hour. The well is shut in after each flow period to allow the pressure to stabilize, as shown here. After the 4th flow rate is completed, the well is produced at a selected constant rate until stabilization of pressure during flow takes place. The last rate may not be as high as that selected for the 4th flow rate of the test. When the results are plotted on log paper, it is seen that the slope of the line, N, is equal to that obtained by the conventional test. However, the position of the line, and thus the value of C, is not correct. That is where the stabilized portion of the test is used. The single point obtained from the stabilized flow rate portion of the test is on the correct line, and therefore we merely draw a line through it, parallel to the plotted line. A typical isochronal test is shown in your course manual.
Compared to the conventional test, this test saves the flaring of gas. It saves time because we don't have to wait for stabilization to occur during flow. This is particularly valuable on tight gas sands where stabilization takes an extremely long period of time.
In 1959, Dr. Katz and others working at the University of Michigan suggested a modification to the isochronal test. They suggested that both the shut-in periods and flow periods for each test could be of equal duration, provided that the unstabilized shut-in pressure at the end of each test be used instead of the static reservoir pressure, P sub R, in calculating the difference of pressure squared for the next flow rate. A typical modified isochronal test is also shown in your course manual. For this test, the actual plot and method of determining the appropriate deliverability curve is similar to that shown earlier for the isochronal test. A best fit line is drawn through the 4 points to determine the slope, and a second line parallel to the first is drawn through the stabilized point.
The values of N and C are found in the same manner as we outlined earlier. The modified isochronal test is used extensively in industry, so let's take a few minutes to be sure that you understand the basic theory behind the test and the procedures used in performing the interpretation.
Turn to Exercise 2 in your manual.
Good work. Now that we're familiar with both conventional and isochronal testing procedures and interpretation, and that we've assured you that industry uses these tests rather extensively, let's see what additional information we can gain from gas well testing.
Specifically, several additional steps may be taken in order to improve the accuracy of the deliverability relationship or gain more information about the well's performance. It can be shown that N and C, which the conventional test assumes to be constants, are in reality functions of such properties as viscosity, temperature, gas compressibility factor, reservoir permeability, net pay thickness, wellbore damage, wellbore radius, and drainage radius. If these factors do not change appreciably, the same deliverability data may be used for the life of the well. In practice, though, the gas properties will change, and so will N and C. In order to incorporate the changes that occur in gas properties with pressure, we introduce the pseudo-pressure or real gas potential. No longer is it necessary to assume average gas property values, and when pseudo-pressure is substituted for pressure in our deliverability relationships, the results will be more accurate. This is especially true where large drawdowns occur. The basic definition and recommended use for the pseudo-pressure concept is found in your course manual. Investigators have looked further at the interpretation of traditional gas well tests and have learned, first, that more information about the well may be obtained if the testing procedures are modified somewhat, and second, that as a means of estimating performance, the AOF plot may be misleading. The conventional well test and AOF plot are misleading because the test does not indicate the degree of near wellbore damage, only the well's productivity in its current state. Turbulence, which occurs near the wellbore, is rate dependent and causes the assumed 4-point line to be, in reality, a curve. The position of the line on the plot changes with the degree of stabilization. In order to gain this additional information and accuracy, investigators have developed the basic equation that represents the radial flow of gas into a wellbore. In doing so, they have included terms for turbulence and skin effect. The equation has been solved for the type of flow tests that are possible on gas wells. One such well test is to shut a well in until its pressure has stabilized, and then open it to flow at constant rate and observe its pressure behavior. If this is done, we may observe 3 states of flow: unsteady state or transient, pseudo-steady state, and transitional. Unsteady state flow occurs during the time when the flow system acts as though it is of infinite extent. Most flow tests are applicable during this period. The duration of this flow period is given by the relationship T equals 360 phi mu c r sub e squared over k, where T is in hours, and r sub e, the radius of the boundary, is in feet. A plot of flowing bottom hole pressure versus time during unsteady state flow might look like this. After the pressure disturbance caused by the flowing well reaches the boundary, the pressure behavior changes. The rate of change of pressure with time becomes constant. This means that our P sub WF versus time plot becomes a straight line. The start of pseudo-steady state flow is given by the relationship P equals 1440 phi mu c r sub e squared over k. The period between the two is referred to as the transitional flow period. If the differential equation describing radial flow of gas into a wellbore is solved for the case where a well is open to flow at constant rate, the solution during the unsteady state flow period will be as shown here. To this basic flow system, and therefore to our basic equation, we should add the supplemental pressure effect caused by near wellbore differences in formation properties. This is usually referred to as the skin effect. Skin is defined as any factor at or around the wellbore which causes an increase or decrease in the pressure drop, as compared to the pressure drop which occurs when the stratum is homogeneous and fully penetrates the sand. As is shown in this illustration, damage from, say, mud filtrate invasion causes an additional pressure drop, whereas a stimulation treatment reduces the pressure drop. A positive skin indicates damage. A negative skin, enhancement. But skin can be caused by factors other than damage or stimulation. For example, partial rather than complete penetration of a wellbore into a formation falls under our definition of skin. So does production through perforations. The near wellbore turbulence that occurs during the production of gas causes an additional pressure drop to that which results from Darcy flow. Such extra pressure drop is considered to be a non-Darcy flow skin, but one which depends on flow rate. The additional pressure drop caused by a damaged zone in the vicinity of the wellbore is shown here. Note that the skin effect is localized and may be significant. If the damage is significant, remedial methods should be recommended. If we incorporate the composite effect of skin, that is, the skin factor that is not rate dependent, S, and that which is, D, into our basic radial flow equation, we obtain what appears here. It should be pointed out that S is itself the composite effect of limited entry to flow and formation damage or improvement near the wellbore. You must discriminate between these two effects before knowing whether a stimulation job will be helpful. Details appear in your manual. The basic assumptions made and the mathematical steps required to reach this solution are also given in your manual. So are the definitions of specific terms and their units. So, if you are not familiar with this equation, we suggest that you stop the video player at this point and work exercise 3 in your manual. In looking at our basic equation, we realize that certain terms are known from basic data, specifically mu, z, t sub r, h, phi, c, r sub w, and other terms are measured during a well test, specifically p sub r, p sub wf, and q sub sc. This leaves us with 3 unknowns: permeability K, or KH if H is not known, skin factor S, and non-Darcy flow coefficient D.
Now we must see how the values of K, S, and D are determined. Let's start with the easiest, K. A drawdown test is one where we shut in a well, allow it to reach a stabilized pressure, and then open it to flow at a constant rate. Pressures are recorded during the flow period. A build-up test may follow a drawdown test. It is a test where the well is flowed at constant rate for a period of time and then shut in. The buildup of pressures after shut-in is recorded.
If we take a closer look at our generalized equation, we note that if the flow rate Q sub SC is constant during a drawdown, a plot of P sub W squared versus T will be a straight line on semi-log paper. The slope of this line, M, is equal to minus 1637 mu z T sub R Q sub SC over KH. And since Q sub SC, T sub R, mu, z, and quite likely h are known, it is a simple calculation to find K. We may also calculate K from a build-up test. In fact, it is usually preferable to do so because it is difficult to achieve a constant rate of flow during a drawdown test. If a well is produced at constant rate for a period of time, T, and then shut in for a period, delta T, we find that a plot of P sub W squared versus the log of T plus delta T over delta T is a straight line with slope M. The slope must be measured on the straight line portion, not during the early shut-in periods when afterflow into the wellbore occurs. So, we see that either a drawdown or buildup test will give us the value of the unknown, K, but that the buildup test is preferred. For convenience, we define a new term, S prime, equal to S plus dq sub SC. S prime may be thought of as a composite skin factor. It is shown in your manual that if we perform a buildup test, S prime may be calculated using the relationship shown here. Note that P sub W squared at delta T equals 0 is the wellbore pressure at shut-in, and P sub W squared at delta T equals 1 is the wellbore pressure 1 hour after shut-in. But note that P sub W squared at T equals 1 is measured on the extrapolated portion of the straight line, as shown here. Because S prime has two unknowns, S and D, we must have two equations for a unique solution. A drawdown buildup test at one rate, Q sub SC1, followed by a second drawdown buildup cycle test at a second rate, Q sub SC2, will give us that unique solution. It should be noted, however, that the well must be shut in before the second test in order to reach original pressure conditions. It is also seen that the required 2 drawdown buildup test sequence is equivalent to the first 2 flow cycles in an isochronal test, except that we must now measure pressures continuously. In summary, then, a simple buildup test will give us the effective permeability, and 2 buildup tests will give us not only K, but also the 2 constants, S and D, of our composite skin factor. Although the composite skin factor could have been obtained using drawdown tests, as mentioned earlier, it is generally preferred within the industry that buildup tests be used and that at least 3 cycles, that is, 3 data points, be obtained. This testing procedure is equivalent to a 3-cycle isochronal test. The S prime versus Q sub SC is then plotted on linear coordinate paper, and the best straight line drawn through the points. The slope of this line is equal to D. The intercept is equal to S. So we now have a more complete method for testing a gas well. Basically, we conduct tests which will give us best fit values for the unknowns, K, S, and D, in our generalized equation. Once we have determined these values, we use the equation to predict future well deliverability and consider whether any remedial work should be undertaken. The AOF of the well will be the delivery rate obtained from the equation when P sub W squared equals 0. A specific example of a well test where this method has been applied is shown in your course manual.
Before proceeding with testing design considerations, let's stop once again and be sure we understand what we have just done.
Turn to Exercise 4 in your notes.
Before discussing field procedures and the reporting of a specific gas well test, there are a few further considerations to be mentioned. Specifically, we wish to discuss the use of surface pressures in our relationships, the time to stabilization, the choice of flow rates, the duration of flow rates, wellbore storage effects, the production of liquids, the choice of measuring equipment, sampling, and safety in testing. Let's begin at the beginning.
Deliverability relationships using wellhead rather than sand face pressures are useful because they are directly related to surface conditions, that is, to the gathering system back pressure.
Off of our Christmas tree, we have also a small looping wire coming off that goes to a deadweight gauge that is a very accurate pressure measurement instrument. And so we measure our pressure at the surface off of the Christmas tree.
So you're measuring surface pressure, and later you'll convert to sand face pressure when you get all this information back to your offices.
Right, to get the bottom hole pressure.
Get the bottom hole pressure.
However, because the difference in pressure between the surface and sand face depends on downhole equipment and flow rates, a relationship founded on surface pressures will not be constant throughout the life of the well. It is recommended, especially at pressures above 2,000 psia, that the fundamental relationship for the deliverability of a gas well be based on sand face pressures, and that appropriate correlations, usually available in existing computer programs, be used to convert sand face pressures to surface pressures, if surface conditions are needed. Appropriate correlations are given in your manual. Specifically, it should be noted that various computer programs are available for gas well testing with multiple options for calculating surface and subsurface pressure. Other programs are also available which calculate pressure drop in tubing strings for both vertical and deviated wells.
In conducting the conventional test, and for the extended period of flow in the isochronal test, the duration of flow must be such as to reach stabilized conditions.
The time required to reach stabilization is usually considered to be the time to the onset of pseudo-steady state flow. Earlier in this program, we saw how that time was estimated. In general, we can say that the time to stabilization will be long for a large reservoir with low permeability and short for a limited reservoir of high permeability. An estimate of stabilization time should be made before a test has begun. If a low stabilization time is expected, a conventional test may be run. But if stabilization time is expected to be long, isochronal or modified isochronal tests must be run. As we shall learn, state regulatory bodies often define rules of thumb estimates of stabilization time of the form less than 0.1% pressure drop in 15 minutes.
You flow at a single rate until you get stabilized pressures, which has some definition in Louisiana, like 1% pressure change or some equivalent like that in a certain period of time. Is that
right? It's 1% in 15 minutes.
In 15 minutes.
Right.
Okay, good. Now,
It should be recognized that such rules of thumb may be in error. In conducting a flow test, the minimum flow rate used should be equal to that required to lift the fluids, if any, from the well. A minimum velocity of 5 feet per second in the pipe is recommended. The rate should also be sufficient to maintain a wellhead temperature above the hydrate point. The suggested minimum and maximum test flow rates are those that result from pressure drawdowns of 5% and 25% of the shut-in pressure. This is approximately equivalent to 10% and 75% of the AOF. The flow rates must not be so high as to cone water into the well from a gas-water contact, nor to cause the production of sand. When a producing well is shut in at the surface, flow from the formation into the wellbore continues for a period of time. This continuation of flow is called afterflow, or wellbore storage, and is caused by fluid compressibility. The wellbore storage time, T sub WS, is given by the expression shown here. It is the approximate time in hours required for the wellbore storage effects to become negligible. Note that V sub WS is the volume of the wellbore tubing and annulus if there is no packer, and C sub WS is the compressibility of the wellbore fluid at mean temperature and pressure. For example, if KH equals 100 millidarcy feet, C sub WS equals 1 times 10 to the minus 3 psi to the minus 1. Mu equals 0.015 centipoise, and there is 2,000 feet of 6-inch ID casing in the hole. Then the wellbore storage time is 8.52 hours. However, had there been 3-inch ID tubing on a packer in the hole, the storage time would have been reduced to less than 1 hour. In most cases, then, the wellbore storage time is short. The duration of a flow test, especially for the flow period of an isochronal test, must be long enough to investigate the formation beyond the near wellbore damaged or stimulation zones. If we wish to investigate a region extending well beyond these zones, say out at least 400 feet into the formation, then we can calculate the minimum time for a pressure transient to reach this distance with the expression shown here. If we assume that the porosity is 0.15, permeability 25 millidarcies, gas viscosity is 0.015 centipoise, the average reservoir pressure is equal to 2,000 psia, and R sub E equals 400 feet, then T sub 400 equals 2.75 hours. The minimum time of the test, then, must be the greater of this value and the wellbore storage time. Many gas wells do produce liquids, be it condensate or water, which cause fluctuations in the rate and pressure measurements. In some cases, long flow times may be needed before the liquid-to-gas ratio stabilizes and test data become valid. Separators are needed at the surface in order to measure gas and liquid production rates.
This separates all the gas away from the liquids, whether it be oil and water or just oil or water, one or the other.
In addition, because correlations of surface to sand face pressures are inaccurate for two-phase flow conditions, bottom hole pressure and temperature measurements are recommended. There are two situations where a single point test on a well is undertaken. The first is where a regulatory agency fixes the value for N in the conventional test, and a single data point is needed to obtain values for C and AOF.
Yeah, the state requires that a one-point test, which is one flow rate, give you volumes of gas, water, and oil you're taking. Now,
So let's talk about that one flow rate where you flow down to a point stabilization.
that's correct. Your flow rate is stabilized and your flowing tubing pressure is stabilized within 1% of the shut-in pressures.
1% in a 15-minute period, or
That
an
is
hour
correct.
period, or
In 15-minute period.
15-minute period. And how long for these type of wells does that normally take? Rough order of magnitude.
It could take anywhere from 2 hours to 5 hours, but usually about 2 hours would be fine over here.
Okay, now for your corporate purposes, you're going to go beyond that.
That is correct. We will run a 4-point test, which means we'll start at the highest rate, which will be in the range of hopefully 3 million a day, and take different measurements at different flow rates, probably 2 million and 1 million a day. This will help us to determine the extent of the reservoir, the deliverability of the well, and will help us in later engineering studies.
The second situation where a single point test is used is in the updating of previous test data. If previous tests have given values for N and the non-Darcy flow coefficient D, then a single point test is sufficient to update values of C and S. This test is often conducted annually as part of a pressure survey. In such cases, the gas is usually produced directly into the pipeline and is not wasted.
Let's stop once again and be sure we understand the fundamentals and the calculations required in the test considerations which we have just discussed.
Turn to Exercise 5 in your manual.
We we have 3 more key topics to discuss: test design, field procedures, and interpretation of results. Let's first of all talk about test design, and then go back to the fellows we were talking to at the very beginning of this program and see how they carried out the field procedures and interpreted the results from that particular well.
Discussion of field testing procedures can be divided into 4 main categories: testing facilities, measurement and sampling, field conduct, and reporting of results. Let's start from the top. The selection of testing equipment is based on the nature of the produced fluids and the type of test being run. The simplest configuration of wellhead testing facilities is that required for wells producing a sweet, dry gas. In this case, the essential equipment, shown here, is a flow rate measurement device, a shut-in and flowing pressure measurement device, a thermometer, gas sampling equipment, and necessary fittings. If a critical flow prover is used, the gas is vented to the atmosphere, unless, of course, regulations provide otherwise. If the gas is to be produced into the gathering system, an orifice meter using a permanent or removable meter run is used. The presence of condensate and/or water in the produced fluids requires more complex testing equipment. Now, in addition to the equipment needed for a sweet dry gas, we will need gas and liquid sampling equipment, line heaters, separation facilities, and liquid measuring devices. If 3 phases are present, then 2 stages of separation are required. For high-pressure wells, more than 1 stage of separation may also be required. The line heater is used to heat the fluids so that hydrates do not form during the pressure drop across the variable choke. An alternative to the heater is the injection of alcohol or glycol into the gas stream. Note here that the gas flow rate is measured downstream of the separator and the various sampling points. For testing sour gas wells, even more equipment is needed. In addition to that mentioned above, a gas meter and flow line to an appropriate flare stack is required. In Alberta, for example, if the gas contains over 1% H2S, it must be flared from a stack at least 12 meters high, and flaring must take place at least 25 meters from the wellhead. Liquid seals may also be needed to protect the gas meter and deadweight tester from the H2S gas. Other measures to protect against the corrosive nature of the gas might need to be taken. Let us turn our attention now to measurement and sampling. We learned earlier that gas flow rate measurement may be accomplished through the use of an orifice meter or a critical flow prover. As turbine and displacement meters have become more accurate, they too have been incorporated into gas well testing. For example, Oklahoma now allows the use of gas turbine meters. Because of our earlier studies on gas flow measurement, we shall only make the comment that it is important that a proper orifice size selection be made prior to beginning the test.
These roll meters here are coming from the low pressure separator measuring the water and the oil.
The meter should be installed upstream of a snap acting valve and with sufficient straight pipe for an accurate measurement. The size of the separator and valve setting should be regulated to ensure sufficient retention time in the separator to reach equilibrium. Gas breakout in the meter will cause errors in measurement. If condensate volumes are measured in the stock tank rather than using a meter, it is important for accuracy that the fluid entering the stock tank is from a low-pressure separator. For accuracy, efforts to recover and measure tank vapors should be made. Water flow rates may be measured with a turbine or displacement meter, or alternatively gauged in the tank. If both condensate and water are gauged in the same tank, then pink tape is used to show water level. If meters are used, a snap-acting valve should be used to ensure sufficient flow to activate the meter. Accurate measurement of pressure, both static and flowing, is of singular importance in gas well testing. Our primary objective, however, is the measurement of sand face pressures. Ideally, this pressure is measured downhole at the sand face or opposite the perforations for the pressure range, using an accurate, carefully calibrated bottom hole pressure gauge. The three basic types of bottom hole gauges are the self-contained wireline gauge, the permanently installed surface recording gauge, and the retrievable surface recording gauge. The self-contained wireline gauge is the one most widely used in the industry. It is lowered into the hole on a solid wire or slick line. The three essential components of the gauge are the pressure sensing device, usually a Bourdon tube, a pressure time recording chart, and a clock. The clock is designed to run and record data on a chart for a specific period of time. If data is needed beyond that time, the gauge must be retrieved, reset, and rerun into the well. A number of companies manufacture and sell these gauges. An Amerada gauge is shown here. Permanently installed surface recording gauges are generally attached to the tubing string. The instrument includes a means for measuring bottom hole pressure and transmitting that value to the surface. Normally, a cable strapped to the outside of the production tubing is used to transmit information. As data is needed, a recorder at the surface is connected and turned on. Retrievable surface recording gauges are similar in most respects to the permanently installed type, except that they are run on a simple conductor wire line. Most use Bourdon tubes for pressure measurement, although some use a quartz crystal. Even though bottom hole pressures are being recorded, it is recommended that wellhead pressure measurements be recorded at all times. Such data can be used as a check on bottom hole data and for wellhead deliverability calculations. We measure surface pressures continuously and have a deadweight tester at the surface. In some instances, for example, where there are mechanical difficulties, highly deviated holes or sour gas production, it may not be practical to run bottom hole gauges. In such situations, wellhead pressures are measured and correlations discussed in your manual are used. All fluids produced at the wellhead should be accurately metered, sampled, and analyzed in order that an accurate recombination is obtained.
Now off of these pots we can take samples to determine what our chlorides are off of the water pot, and off of the condensate pot we can get a sample similar as we did with the gas line and just put it in a jug of some sort, and then we can send that off for some sort of analysis.
Samples are taken according to industry practice, and all sampling points and conditions of sampling should be noted on a line diagram of the wellhead facilities. Liquid samples should be taken at separator conditions so as to avoid the calculations required to convert stock tank volumes to equivalent separator conditions. Of course, reference should always be made to more accurate sample data that might have been collected soon after the well was discovered. Safety enters into all aspects of oil and gas field operations. Gas well testing is no exception. Some elements of safety have already been discussed. H2S is to be flared from a stack or put into a pipeline. Gas is also normally flared unless a critical flow prover is used in a dry gas well. All lines should be pressure tested before the test and properly tied down so they won't move during testing. It is often recommended that a test not be started after dark. Alberta recommends that a minimum 5-man crew, 2 two-man shifts, and a supervisor be assigned to any 24-hour operation. It also requires that 2 sets of breathing apparatus be available on the lease at all times. And, of course, emergency procedures and firefighting capabilities should be fully understood by all crew members before the test begins. You should take time to inform yourself of other local company and regulatory standards and procedures before a test begins, and be sure they are fully observed. Careful observance of safety procedures by you will prevent unnecessary injuries to workers, damage to the producing well, surface equipment, or landowner's property. The field procedures followed during a gas well test are usually those specified by the state or province in which the well is located. A company will often go beyond those required by local regulations, but those regulations usually form the basis of the test procedures. Because regulations differ from state to state, let's take a few minutes to review a specific set of regulations. Many state regulatory agencies and operating companies refer to the Manual of Back Pressure Testing of Gas Wells, published by the Interstate Oil Compact Commission in 1962, as their primary guide to gas well testing. Individual states such as Texas, Oklahoma, Kansas, and the province of Alberta have published their own respective back pressure testing procedures. For illustration here, though, we shall refer specifically to the recommendations found in the IOCC manual. The IOCC manual recommends that the 4-point conventional back pressure gas well test be the standard testing procedure used in determining well deliverability and AOF. In retesting a well, a single point, stabilized test may be used to obtain values for C and AOF. If the conventional test is not practical because the time to stabilization is too long, or because excessive gas must be flared, then either a non-stabilized multi-point test or an isochronal multi-point test may be conducted in order to obtain a value for N. The value of N is then to be applied to a stabilized single-point test to determine C and the AOF. In conducting the conventional multi-point back pressure test, certain procedures and instructions are to be followed. The observed data and calculations are to be reported on the prescribed forms. Vented gas volumes shall be minimized. Record surface pressures with a deadweight gauge. Subsurface pressures with a properly calibrated bomb. Flowing surface temperature should be reported. The IOCC recommended conventional test procedures are as follows. The well should be produced into a pipeline long enough at a high enough flow rate so as to clear the well bore of accumulated fluids prior to initial shut-in. If the well bore is not cleared of fluids, the well may be blown to atmosphere. If no pipeline exists, the well may be blown to atmosphere or flared to remove liquids. The well is then shut in until the rate of pressure buildup in a 30-minute period is less than 0.1% of the previously recorded pressure. This pressure is recorded. The well is then produced for a series of at least 4 stabilized flow rates, and stabilized pressures recorded for each. The shut-in time between flow rates should be minimized. An increasing flow rate sequence is to be used unless a high liquid ratio well or unusual temperature conditions prevail. The lowest rate should be sufficient to keep the wellbore clean. Good data spread is required. Wellhead flowing pressure should not be less than 95% of the well shut-in pressure at the lowest rate, and not more than 75% at the highest flow rate. The flow rate is measured with an orifice meter or critical flow prover. Orifice meter and plates should be calibrated and verified. Barometric pressure should be recorded. Specific gravity of the produced fluids should be determined. Pressures and volumes of produced fluids should be recorded periodically during each flow period. Stabilization occurs when both the flowing wellhead pressure and the rate of flow are constant for at least 15 minutes. At the end of each flow rate, the following data is recorded: flowing wellhead pressure, sand face pressure, rate of liquid production, flowing wellhead temperature, all gas metering device data. The complexity of calculations depends on whether a back pressure equation based on wellhead or sand face pressures is to be used. If the wellhead shut-in pressure is less than 2,000 psig, the IOCC allows a deliverability equation based on wellhead pressures. If the wellhead pressures relationship is to be used, the wellhead static pressure must be recorded or estimated. Corrections to recorded pressures must be made if liquid has accumulated in the wellbore. If the bottom hole pressure relationship is to be used, a pressure datum should be selected at the midpoint of the producing interval open to flow. Sand face pressures at datum corresponding to recorded static and flowing surface pressures should be calculated using appropriate correlations. If subsurface pressures are recorded, they should be corrected to datum. Also remember to correct for any liquid accumulations in the wellbore. You will now have all the necessary data in proper form for plotting. The standard log-log plot of the 4 points is made, and values for N and C determined, as we pointed out earlier. The AOF is found by extrapolation or calculation. If a good straight line cannot be drawn between 3 or more points, the well must be retested. If the same condition exists upon retest, then the line through the best 3 retest data points is to be used. If it is found that N is greater than 1 or less than 0.5, a retest is necessary. If the same condition exists upon retest, then specific values of N equals 1 or N equals 0.5 are used, and a straight line is drawn through the highest flow rate point in the former case, that is, for N equal to 1, and the lowest flow rate point in the latter case, that is, for N equals 0.5. Because of the potential need for a retest, it is important to make preliminary calculations at the well site before the testing contractor is released. All well test data and calculations are to be submitted to the appropriate regulatory agency on standard reporting forms. Other IOCC testing procedures, samples of gas well regulations for several producing states, and a collection of reporting forms are to be found in your course manual. In order to become more familiar with the different procedures that exist in the various states, stop the video player now and work Exercise 6 in your course manual.